Alrighty. So let's get the unimportant stuff out of the way first. What is the value of the first expression? So if we evaluated it, what did you get? Alora?
8.
What?
8.
8. Up or down? Come on, people, you got thumbs. Okay, good. All right, what about the second one? What did you get there? Ryan?
8.
What? Really? Huh, weird. 8. Up or down? Huh. Okay then. So they have the same value. That's interesting. Almost like that was intentional. It's frozen. That's a bad thing. No, it's not. So let's get down to the harder, actually, so the more important work, not necessarily harder work, but this idea of how can we rewrite, okay? How can we rewrite these using exponents? How can we rewrite these using exponents? So pick the one you would like to pick and then tell us how to break it down. But I want you to break it down one step at a time. I don't want you to just like, poof, there's the answer. You know? How can we rewrite these using exponents? All right then, everybody. All right, Kira, what you got? Pick green or peach? Green. Go ahead. Okay, so that's like, boom. I got to the end there, Painter. I want to see one step at a time. How did you get to 16 to the 3 over 4 power? Or, so then does that apply to the peach too? Because the inside is the numerator and the outside is the denominator? Oh, so I don't get that. Could somebody help us get to the green? Okay. Could somebody tell me a way to rewrite the fourth root? How could I write that with an exponent? Ryan? So that would be the power of 1 over 4. The fourth root is the 1/4 power. So fourth root, 1/4 power. That looks like 1/9. Okay. And this makes a lot of sense, because it's not a power. It's the opposite of a power. It's a root, right? Roots are opposite of powers. And so instead of using like the fourth power, right? Instead of using something that says like the fourth power, right? This is the opposite of the fourth power. It's the 1/4 power because 4 and 1/4 are opposites. So we're just using the opposite number to signify root. Opposite, inverse, right? All right. So if I then kind of use my order of operations, I know the 16 to the 3rd is actually the first thing that looks like is happening, right? And then all of that is being raised to the 1/4 power. So how does that help me justify Kira's end result? Over there. Good, everybody else. So Eliana's telling us we're going to take a power to a power, so we're multiplying the powers. So let's see why that rule works really quick. If I had 2 to the 3rd to the 4th, right? Simple example of this. What does that mean? 2 to the 3rd raised to the 4th. And then when I would say, when in doubt, write it out. What the heck does the 4th power mean?
Well, that first itself is in the parentheses, so you do 2 to the 3rd.
What if I don't actually evaluate it? What if I just say it's 2 to the 3rd? I'm just going to write 2 to the 3rd.
I don't understand the question.
I'm not trying to find the value. I just want to rewrite it. I don't want to multiply anything. I don't want to do any calculational work. I just want to write out what it means. I'm going to stick away from calculation.
It would just be 2 to the 3rd multiplied times itself 4 times.
Right? 4th power means I'm going to actually take what's inside of there and I'm going to multiply it 4 times. Right? There it is. Now, this brings us to another exponent rule. When I'm actually multiplying things that have exponential expressions that have the same base, when I'm multiplying powers that have the same base, what do I do with their exponents? I add them. Now, I understand why that rule works. I understand it's a rule. I didn't know that one. Oh, okay, so we're good with that rule. And if we weren't, we could even write it out there, right? 2 times 2 times 2 times 2 times 2 times 2. But either way, when we do this, we can see that we get 2 to the 12th. Which means, what did we really do with these two exponents? Multiplied them. And you can see why. Because this really meant I had 4 of those third powers that were all multiplied. Hence, I had 3 and 3 and 3 and 3. 12. Now, that rule works with simple examples, but it also works with harder ones. So Eliana is telling us that here, power to a power, we're multiplying the exponents. 3 times 1/4 is 3/4. Awesome. So let's do the same stuff with the bottom one. How could I transform the bottom one? What would it look like if I did that? Wow. Lauren, go ahead.
I looked at it in a similar way as the green one, but I took the 16 the root 4 and turned it into 16 times, or to the exponent of 1/4, and then I multiplied that by the exponent.
So you said I raised that to the exponent of root 3, and so then you said, same thing Eliana said with the other one, right? Power to a power, multiply powers. So 16 to the 3/4. So we can see that when we transform both of them, they end up becoming the same thing, which is not a shock, because look, we got the same value. So they should, most likely, or at least it's a good indicator that maybe they're the same thing, and indeed they are. So, what can we take away from this? What can we take away from this? Why did I give you this opener? What can we learn from it? Kira. Yeah, so this whole power to a power rule, right? Multiplying the exponents. Alora.
Simplify fraction exponents.
Talk to me more about that idea of simplifying fractional exponents. Or maybe just break it down for us. When we see a fractional exponent like this 3/4 there, what the heck do those things tell us?
The numerator on a fraction exponent is going to be the power.
Okay, so the numerator of that exponent is like the power. So it's the third power. Got it?
And then the denominator is
The denominator is the root number. So this is that idea of inverse again, right? Like powers and roots, they're opposites. And so, numerator, denominator, kind of those ideas of opposites again. So we can see the numerator is the power. The denominator is telling us the root. So the 3/4 power tells us it's the third power, 4th root. And this is helpful because some of us didn't know this on the homework quiz. What else can we take away from this? Quinn.
But there's kind of 2 different ways you could do the problem.
What problem?
The one up there.
The 16 to the 3/4 problem?
Yes.
Yeah, so and maybe I'm going to make this a little bit bigger, but if I was going to do this problem, Quinn's saying it's telling us there's 2 ways to do this problem. There's 2 ways to evaluate 16 to the 3/4. What are those 2 ways?
You can do the root of 16. What is that called? It's not a cube root.
4th root.
The 4th root of 16.
Yep.
And you can have that to the exponent of 3, or you can do 16 to the exponent of 3 and then 4th root that. Like you could either start with the exponent or start with the root.
So you're telling us it doesn't matter if we start with the root or the power. We can do either one first. Now, if you think about the reason why, these are both powers, right? The 1/4 power, the third power, they're all powers. And so in the order of operations, they're all exponents. They come at the same exact time, right? Doesn't matter which one we do first. And we've proven that it doesn't matter which one we do first right here in the middle. We've kind of shown, by an example, quality example. We could extend that logic to any others. So what Quinn's saying is we have choices here. Think about it. Which one would you prefer? Green or that funky orange color? Which one do you prefer and why? Which one would you prefer in this case and why? Why do we prefer the orange one? Why did I have a stray mark randomly in the middle of my screen? There it goes. Why the orange one? Quinn, take it away because you've done a great job with this.
Thanks, Mr. Feiner.
You're welcome.
I think it's because it's a lot easier to solve. Like, if you can find the fourth root of 16, which is like 2, you just know it. And then you can have that to the power of 3, which is a lot easier than having like 16 3 times and then just like trying to find the fourth root of that in your brain. Like, it just makes it more simple.
Yeah. So it just keeps it simpler, right? I like to think about it, just keeps the numbers. I mean, Quinn's absolutely right. Like, I know the fourth root of 16, or at least I'm more likely to know that than the fourth root of 4,096. So not only is it probably more likely that I know it, but I also like the fact that the numbers are smaller, right? I like to work with small numbers. If I can avoid hard work, I will. Doing it the top way is hard work. Doing it the bottom way, that's smart work. You have to make a choice. Work hard or work smart. We just built a retaining wall. We carried a whole bunch of stone from the driveway to the back, right? And we could have loaded that in pails and pulled those pails back. We could have brought it back stone by stone. But instead, my buddy actually has a trailer, and he has a four-wheeler. So we borrowed that and just put a little kiddie pool in there and shoveled the rock in the kiddie pool and drove it back. Okay? You work hard or you work smart. Sometimes it's actually one and the same. Sometimes it's not. Make smart choices.